Trig equations and trig proofs are my absolute favorite. The difference between the two. With trig equations, we're solving for a variable. Our answer is going to be theta equals pi over 2, or theta equals pi over 4 and 5 pi over 4. With trig proofs, we're going to treat our equal sign like a brick wall and make one side into the other. Like the answer is going to be built in. Don't be scared of it and dread when we get there, because they are they may not be the easiest proofs that you've done in your life, but they are the most algebraic and much easier than like when I sit down to do proofs with geometry students and you're using all of those like property congruence and all of that. Like it's not like that. It's algebra. Okay, so we're solving each equation from 0 to 2 pi. Method 1 is to isolate the trig function and think unit circle backwards. So here's tangent. How do we get tangent all by itself? Subtract radical 3. Yes. Perfect. And split it like we do for my algebra 1 kids. So tangent of theta equals negative radical 3. And now we practice unit circles. So if you're needing to retake the unit circle test, we are practicing those things as we go forward. So I know tangent is radical 3 at my thirds. So I'm going to build in that denominator. And I know tangent is negative. Here is our little diagram that some of you drew with every single problem on your test, and respect. It was beautiful. Tangent is negative in quadrant 2, and my third in quadrant 2 is 2 pi over 3. And quadrant 4, and my third in quadrant 4 is 5 pi over 3. Theta is a variable that you see with angles very, very often. Great, how are we going to get cosine by itself over here? 2 steps. Which thing do I move first, 2 or 6? Yep, subtract 6. 2 cosine of theta is 1. And then what do I do with the 2? Divide. You will see equations once you leave here and maybe in another unit where you cannot do them, they're not unit circle values. Here you know you've solved something incorrectly if you don't get a value from your unit circle. Okay, this is all no calculator, all unit circle values. So cosine is 1/2, also at my thirds. And if this is starting to feel repetitive already, your answers are all going to be on the unit circle, so you know how few values are really there, right? Especially if we now take it to just the places where it's 1/2, or just the places where it's going to be very repetitive. It's tricky for me to design problems where you're going to get some of the weirder answers. Okay, so cosine is positive then. Oops. In quadrants 1 and 4. In quadrant 1, we have pi over 3. And in quadrant 4, 5 pi over 3. So get your trig value all by itself. And do the unit circle backwards. All right, cosecant. I'm going to subtract 10 first here. I'm going to divide by 3. And just like on your test, when you looked at cosecant and you're like, I don't like it, that's fine. Turn it into sine. If cosecant's -2, what is sine of that same angle? -1/2. So if cosecant's 2, sine's -1/2, and sine is -1/2, Well, sine's 1/2 at our sixths. And sine is negative in quadrants 3 and 4. In quadrant 3, that's 7 pi over 6. You can use the trick of the 1 more than your denominator. And in quadrant 4, 11 pi over 6. Just from memory. So that's just, so sine is 1/2. If I'm just thinking first quadrant, sine is my y value, right? So I know 1/2 is one of my smaller values, so it's just going to be up a little. That first angle is pi over 6. So that's kind of, if it was a big angle, like if sine was radical 3 over 2, then I think, okay, that's up here, that's over a little and up a lot, so that's pi over 3. So it's just like that unit circle backwards. So. Good question. What else? We okay? Other question? All right. 3 radical 2 sine minus 2 equals 1. Go ahead and solve for theta.
Actually, that's false.
Okay, I'm going to catch up with you.
I see on my test.
Sine is a number of 1 over radical 2, is it?
Nope.
It's not. What can we make that into?
You can rationalize.
You can. It really is. Sine really is 1 over radical 2. Because 1 over radical 2 is just radical 2 over 2 rationalized. So what's my denominator going to be? The fourth. Yep, sine is radical 2 over 2 at our fourth. Sine is positive in quadrant 1. So it's going to be pi over 4. And in quadrant 2, so my fourth over there is 3 pi over 4.
Let's go.
Good so far?
Yep.
That is basically solving directly. Yeah, all we have to just get your guy all by itself. Find the unit circle back. All right. Next, use square roots carefully. When you think about taking a square root, what do you have to do every time when you're forcing a square root on an equation? What do you need? So if I divide by 4 here, and I have sine squared equals 1 over 4, and then I take that square root, what do I need in front of the square root that's over the 1/4? Plus and minus. So that's the carefully here. Make sure you do the plus and minus, because you're dropping solutions if you don't. Now it's not that you just don't have positive and negative square root of 1/4. You're going to drop the solutions that are on the unit circle as well. Okay, careful here. When we take the square root of a fraction, there's a reason that I did this as a fraction. Square root of 1 over square root of 4. What is the square root of 1? And the square root of 4? Okay, positive and negative 1/2. It's much simpler than it seems, I feel like. And sine is 1/2. What are my denominators going to be? Yeah, 6. And we want all 4 of them. So first quadrant is pi over 6. Second quadrant is 5 pi over 6. Third quadrant is 7 pi over 6. Fourth fourth quadrant is 11 pi over 6. You can write an equation for these solutions, and that's something that's the extension for this. It's actually 2 equations for this guy. So you can't like get the 6th and jump over the 3rd. All right, cosine squared.
12.
So I'm going to add 3 here. Again, it's a really good indicator that you're doing things right if you end up with a unit circle fraction happening, like 1/2 or radical 3 over 2 or radical 2 over 2. If it helps you to remember how to work with that fraction, to do square root of the top, square root of the bottom right away, just so you don't forget to square root the bottom, you can absolutely do that. Square root of 3 over square root of 4. I feel like sometimes the thing that gets left out of these problems is the variable. You guys are doing a really nice job hanging in there with the thetas right now. When you start to get a little more confident and write faster, don't start just writing this. That doesn't mean anything. Cosine of nothing equals 1/2. That's like saying multiply equals 1/2, because cosine is an operator. Okay, so you have to have the angle. If you hate thetas, you're like, I cannot survive this if she makes me write thetas for all of these. Just off to the side somewhere, say let theta equal x, and then use x's or hearts or stars or whatever you would like. It's just a variable. You can use hearts, that's lovely. But make sure you're using some kind of variable, because again, if you don't have that variable there, it doesn't make any sense. Cosine is radical 3 over 2 at our 6ths. Again.
Yes.
All 4 of them, because we have the plus and minus. And the way I'm writing it up here is definitely the way I do it when I'm not like doing anything different in front of you than I do for myself. Like that's what it is. All right, flip your page when you're ready.
I want to see what we did on the last bit. Blow my brain.
Okay. So, all of the solving techniques we know how to solve directly, we know how to take square roots. Here, we're going to start factoring. We're not going to do the quadratic formula with these. You're welcome. We're not going to do complete the square with these. We will graph these later, but factoring is pretty much the most difficult part. If it's helpful to you to not look at these as sines and cosines, you can always substitute in an x for the whole entire thing and do u substitution, or a u, like we did with e to the x. So if you want to say let sine of theta equal u, I don't think it's 100% necessary for the GCF problems, but I'm definitely going to do that when we're doing trinomials, okay? Here's how it would look, just so you can see if you would like it. If you like the look of that instead of the look of the original problem, just don't forget to substitute back in later. That's the danger with using u, because sometimes we get really pumped and we're like, haha, u equals 0. And then we forget, oh, that actually means sine of theta equals 0, and there are differences, like you're not done, because now you have to find where sine equals 0. So if you like this and like the way this looks, that's lovely. I'm going to show you how that looks with sines as well, okay? So that's the u substitution option. Here, I don't mind GCF with sine. So this is 2 sine squares. That's 1 sine. So they have sine in common. So I'm just doing this problem 2 different ways for you. So that means sine of theta equals 0. And sine of theta equals -1/2. If you, like I said, if you like the u substitution, you can u substitute your little heart out. Again, stars, hearts, whatever you want to substitute, they're just variables. But you have to make sure if you do u substitution and get to this point here, you've got to get here from there so that you can say what theta is equal to, because we're looking for theta. So sine is 0 at 0 and at pi, right? It's our outs. And I can't remember if my directions included needing 2 pi. So I'm going to bust back there. Oh, I'm not including 2 pi here, so you don't have to list 2 pi. You can, if you would like. And sine is -1/2. Let's see, sine is 1/2 at our 6th. And sine is negative in quadrants 3 and 4. So it'd be 7 pi over 6 and 11 pi over 6. So if you like u substitution and that makes the problem look friendlier to your eyeballs, definitely do it anytime you need to factor. For something like number 8, you would use maybe like u and v for secant and tangent. You would need to use separate variables for each of them. I'm going to work with secant and tangent to show you how that looks. Number 8 is one of, yeah.
When you do the separate theta.
Yeah, absolutely. Absolutely. As long as you have that list somewhere. It's fine. The secant tangent column here is just one iteration of about 1 million that I've written that you will see. It looks like with this problem that you should divide by tangent to get rid of it. If you divide, you lose the solution. Okay? So anytime you're thinking divide, instead of divide, subtract over and factor. So if you divide by tangent, again, if you divide and clear out that variable, you lose the solution. So we're going to subtract tangent over. What? Okay. And these work just like variables. So when we move that tangent over, it's not a like term with 1/2 secant tangent. Just like x is not a like term with xy. Okay? And now we're going to factor out that tangent because this is just 2 terms. Just like over here, we have 2 terms with 2u squared and u. So we're going to factor out that tangent. And sometimes it's helpful, especially when you're getting used to the way this looks, to kind of write yourself a fill in the blank. So if I started with 2 terms before I factored out a GCF, I need to have 2 terms there in my parentheses. There need to be 2 terms left. Yes, 1/2 secant tangent. Absolutely, yes. That's all multiplication. That's just like 1/2 times x times y. So when I take out a tangent, my first and my next GCF step here, when I factor out that tangent, I'm left with 1/2 secant of x. And when I factor out the tangent from the tangent, I'm left with a 1. And that 1 is really important. So you got to make sure you've got it there. And now we have two things that we can set equal to 0. We can set our tangent of x equal to 0. And we can set our thing in the parentheses equal to 0, 1/2 secant of x minus 1. Just like over here, you could set u equal to 0 and your 2u plus 1 equal to 0. All right, solve. 0, not my face. So I'm going to write it as sine over cosine. Some of you might have tangent memorized, and that's lovely. But if tangent is 0, that means sine is 0, and cosine could be either positive or negative 1, right? It doesn't matter whether you have positive or negative 1 down there. So sine is 0 at 0, and that's pi. Secant is 2, where cosine is 1/2. And cosine is 1/2 at our thirds. So that's going to be pi over 3 for the first quadrant, and 5 pi over 3 for our fourth quadrant. So that's GCF. Solving directly, taking square roots, GCF. Now we're going to trinomial. Are you ready? Okay. This is someplace that I think it is really helpful to do this. Let u equal cosine of theta. And you'll see, I kind of go back and forth. If you look at my work on Canvas, sometimes I'll use u's and sometimes I won't. If you don't factor correctly, you're not going to get the right answer. Like so you have to do however you factor. If you do guess and check, that's lovely. If you do split the middle, remember you have to do 2 times 1. You're not doing factors of -1 there. You're doing 2 times -1 is -2, and then doing your factor tree for -2. My numbers that multiply to -2 and add to -1 are -2 and +1. I've seen some funky factoring. I saw some in the rational functions unit, which is why I'm going a little bit slowly through this. So you change that -1u, that's what you're trying to add to while you're multiplying to -2. Just like in rational functions, not being able to factor here kind of poses your problem kind of from the beginning. So you have to make sure you factor correctly. Here, the first 2, we do this so we can break it in half and just factor each section. These 2 have 2u in common that you can factor out. The first term, if you take out a 2u, you have a u left. The second term, if you take a 2u out, you have a 1 left. The second half of our problem here, you always bring down this positive or negative in the middle. And then if you don't have anything in common, you want to write a 1. Because the way you build your factors is to take this stuff on the outside and make it into one set of parentheses. Take this stuff on the inside and make it into another. Got to be able to factor correctly in order to find the values here. And then you can even go as far as, okay, from here, u is going to be -1/2. From here, u is going to be 1. Well, what was u?
Cosine of theta.
Cosine of theta. not a bad idea to like write your like u equal cosine and then like make yourself a fill in the blank over here to kind of make yourself come back to it. You need to know what cosine is though. And then cosine is negative 1/2 at 2 different thirds. And it's going to be second quadrant is 2 pi over 3. And third quadrant is 4 pi over 3. This fourth quadrant is positive. Cosine is positive 1 at 0 and 2 pi. Don't get sucked into the fact that this one is set equal to 2. It's a trinomial. You got to bring the 2 over and factor. So subtract that 2 over. Get set equal to 0. Use U substitution if that's what you're digging. Back to that bad boy. Alright, so good to here? So sine of theta equals 1/2 is going to give us a good solution. We've done this one several times today. So sine is 1/2 at pi over 6 and at 5 pi over 6. Is sine ever negative 2? No. No, our y value, if we think about our unit circle, our radius is 1. So that's the biggest value that we can have for sine or cosine. So sometimes in designing problems, we're just going to get pieces that don't give you an answer. Just like with logarithms, you're going to look for it more when you're factoring, and it's actually going to stick out to you more than it did with logarithms. So you don't have to plug it back in to figure it out. You just have values you're going to know. Now, for tangent and the reciprocals, those values can be bigger than 1, and we're going to see that a ton when we're graphing. But here, just those 2 values, and you're done. I did make a video for the extension. Look, there's my work from it. So that is, and the directions are right here for that. So that's the extension is what's on the bottom of your paper there. All right. At this point, it would be great for you to find some practice. So if you just flip over, there's some day 1 practice that is just like what we just did. This big problem. Get 1 or 2 done.